Hello statisticians, Mr. Young Saber with Skew the Script here yet again. Today we're going to be talking about food access again, but specifically in the context of a prediction model and the ethics behind it. We're also going to be talking about using technology to analyze regression. Let's skew it. So today's lesson is going to talk about using technology to find regression components as well as to help us interpret computer output from regression models. It is Unit 3, Lesson 4 in our sequence. Today's lesson is also going to focus on this data set in which my former student, Linda, noticed that in a grocery store, local grocery chain, H-E-B, which is the largest grocery chain in Texas, at a higher income area, the H-E-B grocery store location there had more organic food items than her local H-E-B grocery store in her neighborhood. And so she collected data on the average income of the zip codes in which different H-E-B stores are located in San Antonio and the number of organic grocery items offered at those locations. So today we're going to analyze specifically, is it discrimination to provide different offerings to different customers based on data? We're going to finish our lesson there. And let me note right here, we're not talking about H-E-B specifically, but general companies, but we're going to start with talking about this H-E-B data before going there. So this is lesson 3.4. We're going to start with the guided notes. If you'd like to follow along with your own copy of the notes, go to the link listed here. So let's start with one topic we still need to cover about these regression lines before we get into talking about technology, that is leverage and influential points. In this data set, as with all data sets, the least square regression line always goes through one specific point. That point is the mean of your X variable and the mean of your Y variable. So for example, in this case, the mean income was $69,000 among all the zip codes collected here, and the mean number of organic food items at the grocery stores was 52. So if we plot those two and find where they collide, that's the coordinate X bar, Y bar, mean of the X, mean of the Y, and our least square regression line goes straight through that point. Least square regression lines will always go through that mean point for any data set. We can think of the least square regression line as a big seesaw that is centered, or has its fulcrum, or whatever that physics term is, I'm not sure, at X bar, Y bar. One little known fact, superstar chef Guy Fieri, who you know I love to talk about, who's also the mayor of Flavortown, USA, loves seesaws. He absolutely loves to play on seesaws. So here's a bunch of clones of Guy Fieri. They're playing on the seesaw least square regression line. And note that they're positioned in different places. Specifically, one I want to talk about are what we call the low leverage points, or in this case, low leverage Guy Fieris, the ones that are close to X bar, close to the mean central value of our X values. They have less of a pull, less of a force on the seesaws compared to the more extremely placed one, Guy Fieri on the far left, Guy Fieri on the far right. So when we take them all out except for one, we do get a little bit of imbalance in our seesaw, but it doesn't move that much because the low leverage Guy Fieris don't have as much force as the ones on the outside. So low leverage points, ones that are close to the central value of your X coordinates, don't affect the least square regression line much. So let's look in this example. We have a bunch of points that are located around X bar 69,000. If we remove all those points, taking a bunch of points out, note where our line is right now. If we take them out, the line didn't change that much. Went down a little bit, slope decreased, y-intercept a little bit increased, but wasn't a huge change. However, when we have high leverage Guy Fieris, the ones on the far sides are high leverage points, the ones that are way below X bar or way above X bar, they have a large effect if we remove them. Say, for example, we remove this high one. The system here is really imbalanced, and we're going to see, boom, it's going to rotate. The y-intercept will decrease, the slope will become more steep. High leverage points have a high effect, especially on the least regression line's slope. So in this case, we have 3 higher leverage points. These are the neighborhoods where we saw a really high income compared to the average income, and also, coincidentally, a large number of grocery store items. We're really focusing on how the X variable value is really high. So we take off those points, notice where our line is first, take them off, and boom, the line really shifts. Different value in slope, different y-intercept. So the least square regression line really changes when we remove high leverage points. High leverage points are a type of influential point. Those are points that, if they're removed, change the slope, the y-intercept, or the correlation strength, correlation value substantially. So There are three types of influential points: outliers that we looked at before, those change the correlation; high leverage points that we looked at just now that change the slope and y-intercept; and points that are both outliers and high leverage. So let's talk about the different types here. Here's a simple data set. The top one, we see a point that's pretty far away from the other points. It has an extremely high x value compared to the mean. However, it's still in line with the least square regression line. This is a high leverage point because it was a really high x value, but it is not an outlier. And if we were to remove it, we would see the line look like this. The slope changed a lot and has a different y-intercept. So that's what high leverage points do. Now, if we look at the second graph, that green point is pretty close to the central x value, but it does have a high residual. So this is a low leverage point. It's close to that average x value, but it's an outlier, has a high residual, and therefore the correlation is going to be less strong. It's going to lower that R value. Influential points that are both look like this. So this is a point that is high leverage and an outlier. This is your third type of influential point, is both high leverage and an outlier. Has a really extremely high x value compared to what would be the mean x value there. So the line doesn't look like a good fit because of that. It really changed the slope of the line, and has a really high residual, so it's going to be a less strong correlation. So let's talk about using your calculator for regression. We've talked about how to interpret parts of regression. Now let's talk about how to actually do regression given a data set using your calculator. We're talking about TI-84 calculators. There are other steps for Inspire calculators. If you need a copy of a TI-84 calculator, these are some really good emulators that you can find on your smartphone stores that are free. So doing regression on TI-84, here is the data set we've been looking at, and it's also offered in your handout. It's visualized like this. How do I get the least regression line, the R value, and the R squared for this using our calculator? Here are the general steps, and I'm going to post these on the screen right here just for a second so you can see the steps, but I'm also going to go through it on my calculator. So first things first, we got to make sure that all of our stat functions are active. We go mode, and then go all the way down. These are kind of like your calculator settings. And this section that says stat diagnostics, you want to make sure that's turned on. So for me, that's already highlighted, but if not, you want to go over there, press enter, so that on for stat diagnostics is there. Next, you put in your data. So for that, go to stat, edit, and I put in all my data. I put my X values in list 1, my Y values in list 2. So in this case, the average income values are in list 1, the number of organic food items at those stores is in list 2. Then to find our linear regression for this data, we go to stat, calculate, and there are two types of linear regression. There's AX plus B, which is similar to the MX plus B linear equation that we have in Algebra 1. We tend to use in statistics this equation, 8. They effectively are the same, but you just need to know which is your y-intercept, which is your slope. Obviously, the one with the coefficient for x is your slope. The one that's a constant is your y-intercept. So I'm just going to use option 8, linear regression. My X list was list 1, my Y value list was list 2. That's fine. So I'm going to go down to calculate, press enter, and we have everything we need here. The y-intercept value is negative 14.7. That is the constant. The slope value, which is the coefficient for x, was 9.59 times 10 to the negative fourth. So that's about 0.000959. R squared was 0.62 roughly, and my correlation coefficient was 0.79 roughly. So that's how you do it on the calculator. Now let's talk about reading a regression table. So when we do regressions in real statistics life, it's kind of annoying to use calculator, you got to put in all those data points. Instead, you might just download the data set and use a computer for it. And computers put output for regression that looks like this. This is actually from the program R that I use for my regression. So when we take a look at this, and we're going to do it for the same data set we were looking at before, we need to find from this output what is the least square regression equation line, and what are the other features of this that I can pull out. So remember, the y-intercept is a constant, the coefficient is a slope. So if we look at my column here, I'll notice that income, my explanatory variable, my x variable, is listed, and I see two values associated with that. There's the coefficient for the constant's my y-intercept, and there's a coefficient for my x variable, that's my slope. So that's how to get those values out this table. So my least square regression line equation is negative 14.7, the y-intercept, plus 0.001 times x. That's kind of what we got from the calculator as well, to be rounded. These values here are S, the standard deviation of residuals, so that's there for you, as well as R squared. That was easy to pull out right there. So that's how you read a regression table. So you'll be expected to do that on the AP exam potentially. Now, prediction as discrimination. Let's talk about that topic. So say that HEB, the grocery chain in Texas and San Antonio, wants to open 2 new locations. One is in a lower income zip code, mean income about $35,000. One is in a higher income zip code, mean income about $115,000. Based on this least square regression line, how many more organic items are predicted to be offered at the location in the higher income neighborhood? Well, to do this, we need to make 2 predictions. Let's talk about the low income area first. Let's plug in that X value of $35,000. Plugging that in, finding the predicted Y value, it's about 20.3 items. We expect 20.3 organic food items to be offered at that store. For the high income area, we're just going to do the same thing. We're going to plug in 115,000 as my X variable value. High income, plug in 115,000 in, find what it is. The predicted amount is 100.3 items. So the difference between those is about 80. So we expect the high income neighborhood serving store to offer about 80 more organic options than the low income area serving store. Let's discuss this. Let's discuss the consequences of this. So there's a hot topic in data science right now. As data becomes more readily available, there's laws, ethics committee, companies that are trying to forbid companies from using models that make predictions based on demographic data. Specifically, one common example is predicting probability of defaulting on a loan based on your race or gender. So say, for example, in a data set, you find that a certain gender or a certain racial group tends to default on loans more often, then you might use an interest rate in your company that might be different based on the person's background. And that is pure discrimination, and that is outlawed, and most companies are banned from doing that. So say in a more nuanced example, an investigative journalist finds a different supermarket, this is not HEB, but a different supermarket, because HEB is great, we love HEB, actually uses a model to estimate how many organic items it should put on shelves purely based on neighborhood income. The model calls for fewer organic items in low-income areas. So we see a positive linear trend in low-income areas. The model says, okay, we should, for maximizing profit, put less organic food items in stores that serve lower income areas. Here's my question for you all. First, name a reason that this may be considered unethical. But then, if you're the company's CEO, how would you justify using such a model? And then in your own personal view, is this an unethical use of data? Why or why not? That's it for today's Statisticians. Goodbye for now.